Hello everyone, my name is Savita Yadav. My roll number is 205032 and I am going to present on the topic linear transformation. Now first of all we have start with the introduction of linear transformation. Basically what is linear transformation? So linear transformations are the functions of vector space in one vector space V with values which are vectors in the same or another vector space W, which preserves linear combination. So the theory of linear transformation can be applied both to infinite dimensional as well as to the spaces of finite dimensions. In the latter case, that is in finite dimension, matrices are introduced to represent linear transformations. So the matrix representing a linear transformation of V into W depends on the choice of the basis in V and the basis in W. So whenever matrices are used to represent anything, the first problem is to see how a change in the choice of the basis determines a corresponding change in the matrices representing the linear transformation. Now we start with the definition of the linear transformation, how we write its definition. So let V and W are two vector spaces over the same field F. Then a function T from V into W is said to be linear transformation. It is also called linear map from V into W if T C alpha plus beta is equal to C T alpha plus T beta for all alpha comma beta belongs to V and C belongs to F. If V is equal to W, that is the linear transformation T from V to V is known as linear operator. Now the linear transformation T is also said to be vector space homomorphism over F, or it is also called F homomorphism. If it is 1 1, then it is known as monomorphism, and if it is onto, then it is called epimorphism. If it is both 1 1 and onto, then it is called isomorphism. So vector space homomorphism over F is known as isomorphism if it is 1 1 and onto both. So for a linear transformation from T V to W, the set V is called domain of T, and W, which is the image of T defined, is called the codomain of T. So the linear transformation that maps every element of V onto the zero element of W is called zero mapping. So the set of all the linear transformation from VF into WF. VF means that it is over the field F, and W means W is over the field F. Is the space L belongs to V or W. Now we understand what is the range or image of T. So let T V to W be a linear transformation. Then the image of T is defined as, now the range of T is equal to beta belongs to W such that beta is equal to T alpha where alpha belongs to V. It is denoted by IMT, which is the short form of image, and RT, that is the range of T. Now we understand what is the properties of linear transformation. As we know there are several properties, now we will discuss some of the properties here. So let VF and WF are two vector spaces and T be a linear transformation from V to W. Then for the first property says that T of 0 is equal to 0 dash where 0 belongs to V, comma 0 dash belongs to W. Now the second property is that T of minus alpha is equal to minus T alpha for all alpha belongs to V. Now the third property says that T alpha minus beta is also written as T alpha minus T beta for all alpha comma beta belongs to V. Now the last property is T summation of Ci alpha I from I to n is equal to summation of I 1 to n Cit alpha I for all alpha I S belongs to V and Ci dash S belongs to F. Now what is the proof of the first property here? The proof is shown, that is T alpha T0 is equal to 0 dash comma 0 belongs to V and 0 dash belongs to W. Now starting with the proof, let alpha belongs to V, so we get T alpha belongs to W. So 0 belongs to V and T alpha belongs to W. We get T alpha plus 0 dash is equal to T alpha. Now we write it as T alpha plus 0 dash is equal to T alpha plus 0. We know that alpha is equal to alpha plus 0. Now we write as T alpha plus 0 dash is equal to T alpha plus T 0. So by left cancellation law we get 0 dash is equal to T of 0. Now it is the proof of this first. Now the second proof is that we know that T minus alpha is equal to minus T alpha for all alpha belongs to V. So here let A alpha belongs to V, then we know that T minus alpha is equal to T. We write minus alpha as minus 1 multiply alpha. We take common minus 1, so we get minus 1 T alpha. So minus 1 multiplied by T alpha, we get minus T alpha. It is the proof of second part. Now what is the third proof is that T alpha minus beta is equal to T alpha minus T beta for all alpha comma beta belongs to V. So here we write T alpha minus beta, which we also write as a T alpha plus minus beta, where alpha and beta belongs to V. By separating this, we get T alpha plus T of minus beta. We write this as T alpha plus minus T beta, which is from the second property which we derived earlier. Now we get T alpha minus T beta. Now the fourth property is that T of summation I to 1 to n Ci alpha I, which is equal to summation I is equal to 1 to n Ci T alpha I for all Ai belongs to V and Ci belongs to F. So this result is proved by the induction. We earlier studied the induction, then we applied it in this property. So let T summation I is equal to 1 to m Ci alpha I, which is equal to summation I is equal to 1 to m Ci T alpha I. So for we proved that m plus 1, that's we prove it is for m plus 1. So for m plus 1 we have T C1 alpha 1 plus dash 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 plus Cm alpha m plus Cm plus n alpha m plus n. So we by this we get T bracket में C1 alpha 1 plus dash 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 Cm alpha m plus Cm plus 1 alpha m minus 1. Now we write C1 alpha 1 plus dash 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 Cm alpha m as T bracket में alpha I is equal to 1 to m Ci alpha I, and remaining this one Cm plus 1 we write this as a Ci alpha I, summation of that is this, and Cm plus 1 and alpha m plus 1 we write this Cm plus 1 alpha plus 1. Now by taking common we taken out, so we get alpha this summation I equal to 1 m Ci T alpha I plus here Cm plus 1 T alpha m plus 1. Now we get summation I is equal to 1 to m plus 1 Ci T alpha I. So for m is equal to 0, we know that T C1 alpha 1 is equal to C T alpha 1. Here this is a condition. Then from the equation second, that is this is the second equation, here last one, and this is the equation third. So from these two equations second and third, we can say that the result is true for all n, that is T summation of I equal to 1 to n Ci alpha I is equal to summation I is equal to 1 to n Ci T alpha I. So here we all proved that all the four properties of linear transformation. Now what is the example of linear transformations? So first example is that explain whether the transformation T r square to r cube T x comma y is equal to x plus 1 comma 2y comma x plus y is a linear or not. Now we prove it that, so we have r square to r cube be a transformation. This is given in the question. So let we take alpha is equal to a1 comma a2, beta is equal to b1 comma b2 belongs to r square. These two belongs to alpha and beta belongs to r square, and c belongs to r. Then T C alpha plus beta is equal to T bracket में C A1 plus A2 plus B1 comma B2. This is the definition of the linear transformation which we studied earlier in first slide. Now we get T. We solve this at T CA1 plus B1 comma CA2 plus B2 because we know how to open it. Now we get CA1 plus B1 plus 1 comma 2CA2 plus 2B2 comma CA1 plus B1 plus CA2 plus B2. By solving this, then we taken out C common, then we get CA1 plus 2A2 comma A1 plus A2 plus B1 plus 1 comma 2B2 comma B1 plus B2. Now we write is at Ct alpha plus T beta, which is equal to Ct A1 comma A2 plus T B1 comma B2. Then we get C A1 plus 1 comma 2 A2 comma A1 plus A2 plus B1 plus 1 comma 2 B2 comma B1 plus B2. Then we get Tc alpha plus beta is equal to Ct alpha plus T beta. This is the definition, but here we get Ct alpha plus T beta, which is not equal to Ct alpha plus T beta. So by this condition we says that Tc alpha plus beta does not equals to Ct alpha plus T beta. Hence T transformation r square to r cube defined by T x comma y x plus 1 to y x plus y is not a linear transformation. Now here some of the application of the linear transformations are that a specific application of a linear maps is geometric transformations such as those performed in computer graphics, where the translation, rotation and the scaling of 2D or 3D objects is performed by the use of transformation matrix. And the linear mapping is also used in the mechanism of describing change. For example, in calculus, we know that in calculus corresponds to derivatives, or in relativity used as a device to keep track of the local transformation of reference frames. The another application of these transformation is in compiler optimization. What is it? Is in compiler optimizations of nested loop code and in parallelizing compiler techniques. So this is all about the linear transformation. Thank you, sir.